Hello, calculus callers. Today we're going to be learning skill 3, which is on limits graphically. So last class we looked at evaluating limits from table of values and getting those from the table of values. And now we're going to kind of guide you on how to find the limit from a graph. And a nice thing about connecting graphically is we can also think about this concept that's going to be becoming very important in the next few weeks of continuity. So I want you to be thinking about the continuity of a graph in the back of your mind as we kind of go through this lesson today. All right, so what is a limit? Well, a good definition of a limit is that it is the y value of a function as it approaches from both the left and the right side of a given x value. So I really like example 1 because it gets us connecting to continuous and not so continuous functions and making the connections with the idea of a limit. So on the left here we have a very nice, well-behaved beginning of algebra 2 parabola. Nice and continuous. And what we see here is right at -3, that y value is exactly 4. And when we're immediately to the left of -3, or immediately to the right of -3, we are pretty much right at about 4. It's not exactly 4, but it's very, very close to 4 the closer we get to -3. So this is a well-behaved continuous function, and we can kind of see that evaluating the function at -3 and computing the limit is the same thing. Now here we have in pre-calc what you call like a removable discontinuity, where it's just like a hole. And if we plug in -3, we see that it would not work. So that's D and E for does not exist. However, if we go right before -3, we're about 4, and right after -3, we are about 4. So you may want to, when you're taking your notes here, just sketch the rough graph. So you could even, as you're sketching and making your notes, you could put -3 here, you could put 4 here, and just like the general shape, and then just sketch the curve each time. Now over here we actually see that the function is defined, but it's defined at a different point right at -3. So if we plug in -3, we get a 1. However, right before and right after -3, we are approximately at 4. So that's how we're doing that limit graphically. Now, these graphs over here, these are when we kind of have those jumps and those skips. So if we're plugging in -3, we have that solid dot. This is your piecewise function. So the y value of that solid dot is 1. And then the limit as x approaches -3, we see that on this side, it's like 4 for the y value, but on that side it's 1. So the limit is actually D and E because the left and the right do not match. Ooh. And we can kind of see the same thing on this example here too. So that would also be a D and E, even though when we get that solid dot right at -3, it would be 2. So I really like this example because you can see the whole spectrum from continuous to discontinuous, and having like the removable discontinuity in the middle. And some of you may even see a pattern about, how does limits and evaluating the functions relate to continuity. And if you're starting to look for some patterns, you're thinking in the right way. All right, so now we're just going to kind of formally define what a one-sided limit is graphically. So one-sided limit is the y value a function approaches as you approach a given x value from either the left or the right side. So I always like doing the one-sided limits first and seeing if they match up. So on this example over here, right before -3 from the left side, we can see that we're pretty much right at a -1 for the y value, approaching that -1. And then from the right side, we can see that that y value is approximately going to be 2. But the two-sided limit does not exist. Now, during the school year, if we had in-person school, this is what my typical limits graphically test question looks like. You're evaluating, combinations of left and right-sided limits, and two-sided limits as well. And I mixed in evaluating the function, kind of like an Algebra 2 pre-calculus type of exercise embedded in there too. Delta Math, I'm just going to give you one-sided and two-sided limit skills. And it will be kind of like one limit at a time. So I'm going to kind of demonstrate my thinking here on example 3. So on the left here, it says the limit as x approaches -2 from the left. So I'm going right to -2, a little bit to the left of -2, and I see that that y value is 1. So the good news is if you're able to read it right off the graph, and you have the concept of that limit being just a little bit to the left, you get the answer immediately, and then you can move on. Now let's go a little bit to the right of 2. Right about there, a little bit to the right, and we are at about -2 on the graph. And I think it's always best practice to do the one-sideds before your two-sided limits, but we can actually say for part C pretty confidently that the two-sided limit does not exist. And if you really want to make me happy, you could say that it does not exist. Because the limit as x approaches 2 from the left of f of x does not equal to the limit as x approaches -2 from the right of f of x. And if you have that in an explanation, you're actually showing mastery on using limits to define continuity, which is a skill that's going to be a few weeks into the future. So I'd like you to kind of start thinking this way right now before it's too late. All right, part D, we're going to go to the limit as x approaches 1. So here we have a nice removable discontinuity. So we could see that if we plugged in that black dot into the white dot, we'd have a continuous function. And we could see immediately to the left and the right of 1 that our y value is approximately 1 on both sides. The limit as x approaches 0. Now, if we have something that's nice and continuous, like this type of situation, we can just take the y value. So at 0, that y value is -2. And then I have the limit of 3 from the left. Now, this is nice and continuous. So as x approaches 3 from the left or right, you're having that y value at 5. And then we do the limit as x approaches -1. Again, nice and continuous here. We could see what its y value is, and that would be -3. And then I have the limit as x approaches -3. And this is also a continuous, so the two-sided limit, does exist, matches with the one-sided limit, and that y value is 0. And in f of -2, I just take that black dot. So I find that black dot. So we're looking for black dot, if we're looking at like a piecewise function. And that y value would be 1. And f of 1, well, that y value skips down to -2. Now, if you're looking for maybe a way to challenge yourself a little bit, I'll leave this slide up here for the next 30 seconds or so. You could even pause this video if you want more challenging problems for yourself. Some of my students last year got really into a problem like example 4, where I actually give you conditions where I say, okay, I want you to sketch me a graph of a function that meets all these requirements. So it has to have, when you evaluate the function at 3, put in an x value, you get a y value of -1. The two-sided limit as x approaches 3 has to equal 4. And if you're looking, to have a good challenge and kind of think critically about these limits graphically, maybe even beyond the level of your Delta Math videos, these two problems would be a really good opportunity for you to do. So that is limits graphically. So I wish you good luck in copying your notes, and we'll see you for some Delta Math tomorrow.